Alright guys, the next quiz is over atoms and sig figs. So the next two videos are just covering those two topics. The atom is what we're covering first, so just kind of looking back at some history. Remember, John Dalton's atomic theory was kind of our original theory on atoms and what atoms were. He said that everything was composed of atoms, that all atoms were identical, or atoms of the same element, were identical on size, mass, and other properties. Remember that this guy is really no longer true now that we have new data to support otherwise, but it was true at the time. He also said atoms cannot be subdivided, created, or destroyed. Again, this is no longer true, though it was at the time. We now have radioactivity, which can subdivide atoms through fusion and fission. Okay, atoms of different elements combine with simple whole number ratios to form compounds that should be formed, not from. And then a chemical reaction, atoms can be combined, rearranged, or separated. Okay, so that's just our atomic theory. Again, the two ideas that are different from Dalton's between modern atomic theory is the idea that atoms are identical. We actually do have atoms of the same element that are not identical. It's called isotopes, and we'll look at that in just a minute. And then atoms cannot be subdivided. They can, just not in ordinary chemical reactions. They can in radioactivity reactions. Okay? All right, just doing again a little bit of history. Remember, J.J. Thomson was the first person to discover that there were subatomic particles in the atom. He actually discovered the electron using his cathode tube. Okay? And then we have his model, which is a plum pudding model. Because he was able to determine that the atom had a negative subatomic particle in it, that means there had to be some type of positive charge to cancel out the negative charge. The idea behind it is matter is neutral, meaning if there's a negative, there must be a positive. So he came up with this model of a sphere that was positively charged. The sphere itself was positively charged. And then there were these electrons that were negatively charged scattered throughout the sphere. It's kind of like a chocolate chip cookie where the dough is the positive part and the chocolate chips are the electrons, the negative parts. Okay, Rutherford came on a short while later, and what he did was the gold foil experiment, meaning he shot alpha particles at gold foil, and then they went through the gold foil, or they bounced back. Okay, when they bounced back, that told him they were hitting something hard and dense, and this is the first idea of a nucleus. Okay, he said the fact that it was bouncing off was just like a shell, like a gun shell, bouncing off a piece of tissue paper. So that's kind of this idea of why it was so earth-shattering, the fact that an alpha particle was bouncing back. What this told us is that the nucleus was very small, the nucleus was very dense, and that it was positively charged. Alpha particles are positively charged. Remember, alpha particles are 4 to He, meaning they are a helium nucleus with a mass of 4, 2 protons, 2 neutrons. There's no electrons. So the fact that they're bouncing off something or being reflected by something means they were hitting something else that was positive, which they did not want to be around. Basically, same charges. Okay. To review the subatomic particles, we have electrons, which were found by J.J. Thomson. They exist in the electron cloud. You have protons and neutrons that were eventually found by Chadwick as well as Rutherford, and they were both found in the nucleus. The charge of electron is -1, charge of proton is +1, and a neutron is, of course, neutral. In terms of average mass, or mass in general, an electron is 9 times 10 to the negative 31st kilograms, whereas a proton is 1.6 times 10 to the negative 27th. So looking at the difference in this mass, you're talking 1,000 times difference if you think of exponents. Okay, so that's why we consider the electron's mass to be 0 or negligible in compared to protons and neutrons. Typically what we say is a proton has a mass of 1 AMU, as does a neutron, and an electron has a mass of 0 AMUs. Okay? Alright, isotopes, I mentioned that earlier. Elements that atoms of an element that are different is due to the number of neutrons. They're identical in the same number of protons, but they're different in the same number, or different number of neutrons. Protons will be the same for the fact that they're neutral. Electrons will be the same, but the number of neutrons will be different. So this is kind of giving you an idea. A typical hydrogen 1 atom is called protium. It has 1 proton, 1 electron, 0 neutrons. Okay, that's a typical hydrogen atom. We then have deuterium, which is hydrogen 2. Remember that the dash number at the end of it means that's the mass of that particular isotope. That's how we identify them. Deuterium has 1 proton, 1 electron, and 1 neutron. And then you have tritium, which is a mass of 3, 1 proton, 1 electron, 2 neutrons. They both have 1 proton and 1 electron. These are all the same element. Remember, protons I call the DNA of an atom. That's what identifies them or makes them distinct, is the number of protons. That is literally what makes them that particular element. The electrons are the same as long as they're neutral to the protons. The neutrons are what vary, and if neutrons vary, we have isotopes. Okay? Those isotopes can be found in different proportions in nature through percentages. So just to give us an idea of how to calculate atomic average masses, remember the masses on the periodic table have decimals after them. They're not pretty little whole numbers like what we see with like carbon 12, carbon 13, carbon 14. These decimals, or the decimal on the periodic table, is coming from the average of all of these. So the fact that carbon 12 is 98.89%, carbon 13 is 1.1%, and carbon 14, which is a very small percent, is less than 0.01%. Now, just to remind us on how we calculate this, we're going to take the percentage, turn it back into its decimal form. So 0.9889 is our first number. Sorry, that's terrible. Let me rewrite that. 0.9889. We're going to multiply that by that particular atomic mass, which is 12. We're going to add that to the next atomic masses, percentage, and mass. So 1.11 becomes 0.0111 times 13. And then the same thing for the last one, 0.0001 times 14. Once you add all this up, that's where the 12.011 came from. Okay, and again, if you look, they all have the same number of protons, just different number of neutrons because they are isotopes. Another way you need to get used to seeing atomic symbols is that instead of it being carbon 12, it might have a number with a symbol. Okay, if the number is on the top left, that is the atomic mass of an isotope. Sometimes this will also have the atomic number underneath it, so it might say 12,6 carbon, because carbon's atomic number is 6. So just to make sure you understand those symbols. Okay, again, we have atomic number and protons are equal because, again, I call that the DNA. That's what makes them distinct. Okay, and let's just try filling out one of these tables. Okay, so oxygen we know. Here, this oxygen has 10 neutrons. Well, if I look on the periodic table, oxygen has an atomic number of 8. Well, that is my number of protons. Okay, my mass is my protons plus my neutrons, because remember, electrons have a mass of 0. So 10 plus 8 is 18. So my mass number for this guy is 18, which will also go over here because this is oxygen, 18. Okay, and the electrons will match the protons. Same thing down here, 33 is the number of electrons. Protons and electrons will equal. The numbers of protons and neutrons will add up to equal your mass. So 33 plus 42 is going to be 75. Now the way we identify it, because notice there's no element over here, is we use protons as our atomic number. Well, element 33 is arsenic. So we're going to say arsenic, 75. Okay, and the last one here, we have our protons, 15. This is the number of electrons. We're given an atomic mass here, which means to find the number of neutrons, we have to subtract our protons from our atomic mass. So 31 minus 15 gives us 16 neutrons. And again, we use our number of protons to find the element. And in this case, it is phosphorus. Oops, let me spell it correctly. Okay, and that's about it for atoms.